Hello everyone. Our work MFuseNet is for robust depth estimation with learned multiscopic fusion. Today, I will first introduce what is multiscopic vision and its difference with stereo vision. Then I will describe our method in this multiscopic structure. Finally, I will present some experimental results. Our contribution concerning the multiscopic perception system and multiscopic fusion method are summarized here. First, we design a regulated perception system for accurate depth estimation. The system captures multiscopic images with a coplanar, parallel, and semi-parallax structure using a monocular camera. Second, we propose a novel learning-based method for multiscopic cost-volume fusion. The proposed model obtains more accurate depth maps than previous methods do. Thirdly, we generate a synthetic multiscopic dataset using a 3D rendering engine for training. With only tens of images, our lightweight network could be trained and generalized well to real-world scenes. Okay, first let me introduce what is multiscopic vision. Understanding surrounding 3D information is very important for many robotic applications such as manipulation, exploration, or navigation. Usually, this is achieved by stereo camera, structured light sensor, or ToF sensor. But these are expensive compared to a monocular RGB camera. Researchers have been working on depth estimation with a monocular RGB camera for a long time, but the accuracy is not that high. While almost all prior works on monocular depth estimation assume passive sensing, that means camera motion is uncontrollable, such as structure from motion or multi-view stereo. We are wondering if we can obtain more accurate depth estimation with a single RGB camera combined with controlled motion. We take images at aligned camera positions. We refer to the problem of depth estimation with multiple images captured at aligned camera locations as multiscopic vision, as analog to stereo vision with two horizontally aligned images. For stereo depth estimation, a 3D point X projects on two cameras, generating X and X prime on the horizontal axis. Then the depth is inverse to the horizontal disparity of these two pixels. Thus, if we can find the pixel correspondence, then we can get the disparity, then we can simply get the depth. However, this stereo vision structure suffers from many problems like the occlusion, the featureless region, or the reflection. So we propose our multiscopic structure for more robust depth estimation. Taking a 3-camera multiscopic structure as an example, these 3 cameras are parallel, coplanar, and with the same baselines. Now the 3D point P projects on these 3 cameras generating 3 pixels on the horizontal axis. The disparity between left pixel and the center pixel, and the disparity between right pixel and the center pixel should be exactly the same. This is a very strong constraint which can be used to optimize the depth estimation result. With this idea, we command the robot arm to move the camera along the horizontal axis or the vertical axis, such that all images are flat coplanar, parallel, and with the same parallaxes. Thus, the searching for pixel correspondence can be conducted only on horizontal or vertical axes. And the disparity for each pixel in every surrounding images should be the same. Also, the occlusion problem, which troubles stereo vision for a long time, is no longer a problem, because the point invisible to one view can be perceived by other views now. Okay, now we have the multiscopic system. It's time to move from stereo algorithm to multiscopic algorithm. Let's begin with a simple stereo algorithm. To find the pixel correspondence, we calculate the color similarity between the block in the right image and the block in the left image. This similarity serves as a cost to build up a cost volume. But for multiscopic vision, the matching is between the center image and all surrounding image. Thus, there are multiple costs now. So the key question is how to fuse them. One naive idea is maybe taking the average or taking the minimum. But in the experiments, we find they are not that good. So we propose a heuristic theorem. First, we sort these four costs and remove the largest one, which is very likely to be a bad matching. Then we remove the second one if it's too large, and then we take the average of the remaining costs. With this heuristic theorem, we extend the stereo graph cast to multiscopic graph cast by changing the data term and changing the smooth term. The smooth term now considers the smoothness in all images. From the results, we can see from stereo graph cast to multiscopic graph cast, the depth map is more accurate and there are less noise, especially in reflective metal tabletop and occluded areas. However, heuristic theorem cannot be sufficiently sophisticated, and it may introduce human bias. Sometimes the prior knowledge can limit the performance. Considering the feature analysis ability of deep networks, we try to seek assistance from learning methods to fill these cost volumes. So we propose a FuseNet to do the fusion. To our knowledge, this is the first time to do cost volume fusion using learning method. Each cost volume is first fed into the 3D scaling layers to extract features. Then these features are concatenated as the input to a network similar to 3D UNet to generate the disparity prediction. With the 3D UNet architecture, information at different scales can be processed to incorporate both local and global information. Since the size of cost volume is large, we only use 4 feature channels, such that the number of parameters in this network is only around 10,000. A compact network makes it easy to train and be generalized to unseen scenarios well rather than overfitting the training data. Since there is no available large dataset for multiscopic vision to train our network, we synthesize a dataset with hundreds of scenes using 3D render engines. For each scene in our dataset, there are 1 center image and 4 surrounding images. Each color image has its corresponding ground truth disparity map. This dataset actually can be used in many other applications beyond multiscopic depth estimation, like multiscopic super resolution or multiscopic view synthesis. We only use 27 scenes to train the lightweight FuseNet. Although the number of scenes is small, the network can be well trained and perform stably on unseen scenarios because our network is very lightweight. Compared to with only 1 cost between the stereo image pair, the result after multiscopic cost fusion is cleaner and smoother, and the object boundary appears sharper. Okay, let me show some experimental results. We evaluate our method on the Middlebury dataset. From the results, our method obtains better disparity map. And from stereo to multiscopic, the error is reduced a lot. We also compare our method with previous classic fusion methods and evaluate our method in a real-world application, this reflective workpiece. The results show the multiscopic method can perform well in these hard scenarios because the reflective surface is hard for traditional stereo vision. More results can be seen in the paper. That's all. Thank you.